Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 3, Lesson 5 on piecewise linear functions. This is a topic that you probably saw in Algebra 1, but it's been a little while. So we're going to review how you create and interpret piecewise functions in general, and specifically piecewise linear functions. All right, piecewise defined functions. Now, functions expressed algebraically can be complicated and involve different equations for different portions of their domains. I mean, that makes sense, right? Because all a function is a rule that's going to give you an output for a given input. It doesn't mean that you have to have the same equation for all the different inputs. These are known as piecewise function because, they come in pieces. If all the pieces are linear, right, equations of lines, then they are known as piecewise linear functions. Very kind of easy to understand term, and let's take a look at one in exercise number 1. Consider the piecewise linear function given by the formula f of x equals x minus 1 for negative 3 less than or equal to x less than 0, and 1/2 times x plus 4 for 0 less than or equal to x less than or equal to 6. All right. Let's talk about this a little bit, right? So this is the classic way that piecewise functions are shown, right? And it's really we want to think about it as y equals x minus 1 for all the x values in this interval, and y equals 1/2 x plus 4 for all the x values in that interval. Let's take a look at letter A. Evaluate each of the following: f of 2, f of negative 1, and f of 0. See if you can remember how to evaluate a piecewise function for various inputs to the function. Pause the video now and see if you can come up with these function values. All right, so basically, right, normally when we have a function defined using a formula, we simply take the input and we substitute it into the formula. But here we have two formulas, so we have to make a decision about which one x equals 2 gets substituted into. And for that, we simply look at these domain intervals, right, intervals for the inputs, and we say, well, 2 lies in this domain interval because it's between 0 and 6. So for f of 2, I'm going to come up here, and I'm just going to say that's going to be 1/2 times 2 plus 4, which is 1 plus 4, which is equal to 5. So f of 2 is equal to 5. On the other hand, negative 1 falls in this particular interval because it falls between negative 3 and 0, and therefore I'll use this formula. So f of negative 1 is going to be negative 1 minus 1, let me just put a little dashed line there, which is negative 2, so f of negative 1 is equal to negative 2. Now, probably the trickiest ones are the x values that are sort of at the cutoffs of the formulas, right? So 0 is either in this interval or this interval, and clearly it's in this one because this interval is x is greater than or equal to 0, whereas this one is all values of x all the way up to 0, but not including 0. So for f of 0, I have to use this formula, and that's going to be 1/2 times 0 plus 4, which is going to be 4. So the first thing that you have to be able to do with any function, whether it's represented with a formula, a graph, a table, or anything else, is be able to evaluate outputs for given inputs. Now let's talk about letter B. Create a table of values below and graph the function. Awesome. Well, one thing we can do is we can already fill in some of the values. For instance, f of 2 is equal to 5. So I can put a 5 right here. F of negative 1 is equal to negative 2, so I can put a negative 2 there. And f of 0 is equal to 4, so I can put a 4 there. What I'd like you to do is take a moment now and use the definition of the piecewise function to fill in the values for x equals negative 3, negative 2, 4, and 6. Pause the video now and take a few moments to do that. All right, well, negative 3 obviously falls into this interval. Negative 3 minus 1 is negative 4. Negative 2 also falls into that interval. Negative 2 minus 1 is negative 3. 4 falls into the second formula, so that's going to be 1/2 times 4, which is 2, plus 4, which gives me 6. And then 6 falls into the second formula as well, or the second interval. 1/2 times 6 is 3. 3 plus 4 is 7. All right, now, how do we plot this? Well, like most things, what we're going to do is we're going to plot these points on this grid, but then let's talk about how we connect them with lines. So let's go ahead and do that together. I've got -3, -4. I've got -2, -3. -1, -2. 0, 4. 2, 5. 4, 6. And 6, 7. All right, so we've got these points, and now we have to kind of think about what's going on here. Now, one last thing to consider is that this formula applies for all values of x all the way up to 0, but not including 0. Now, you might say, well, I did that because I took it all the way up to -1, except there are even x values, right, between x equals -1 and x equals 0. For the moment, right, if I put x equals 0 into this formula, right, I will get y equals -1. Now, the graph or the function doesn't actually apply there, but it applies all the way up to there. So what I'm going to do is at 0, -1, I'm going to put an open circle. All right, now, given how small the video probably looks to you, that may even look like a closed circle, but it's an open circle there. So what I'm now going to do is I'm going to connect all of these with a straight line, and then I'm going to jump up to here and connect all of these with a straight line. I am not going to put arrows on either this end or that end because the function begins at x equals -3 and it ends at x equals 6. So it would be inappropriate to have an arrow pointing in this direction or this direction, and certainly would be inappropriate to have arrows here or here. All right? But there we have it, right? And we definitely have like a jump here, which is kind of interesting. And we're going to start kind of looking at how that affects some answers once we get into letter C. I guess I didn't really need my ruler, or maybe I should have used my ruler to make those a little bit straighter. Let's take a look at C. Give a y value that is between the minimum and maximum values of the function that is not in the range of the function. All right, so the minimum y value, right, is y equals -4, and the maximum y value is y equals 7. And maybe just let's write those down just for a second. Y min is equal to -4, y max is equal to 7. But I want a y value that is between those two that's not in the range of the function. So it's easy enough to be like, well, y equals -10 is not in the range of the function. But I want a y value that's in between these that isn't in the range of the function. Pause the video now and see if you can come up with at least one of those values, and there are an infinite number of them. Well, right here we have what we call in math a discontinuity. You don't need to worry about that term right now, but the graph is discontinuous, right? We have to lift up our pencil to go from this point to this point. Any value of y between these two does not exist in the range because there's no value of x that will give us that value of y. So any value between y equals -1 and y equals 4 would work. And let me just write this down. Any value between y equals -1 and y equals 4 works. So, for example, y equals, let's say, 2. Y equals 2 has no x value that will result in that y value. And that is the definition of the range, right? The range is all outputs for which there is an input that will result in that output. But there is no value of x that will result in a y value of 2. And that leads us to the final question in this problem, letter D. State the range of f using interval notation. All right. Now, ranges are a little bit more difficult, as are domains, when the function is discontinuous, all right? Now, let's build this thing, though. Let's not worry about sort of the upper portion. I can't really even see it right now on the screen. Let's just worry about this portion. This portion of the function goes from a y value of -4 to a y value of -1, but the y value of -1 is not included. So I'm going to say that's -4 to -1, and remember with interval notation, if we do not want to include a value, but we want to include everything up to the value, we use a parentheses instead of a square bracket. Now let's talk about this sort of like upper level. Up here, we start at a y value of 4 and we go to a y value of 7, and both 4 and 7 are included, so we could say this. Now, how do we join the two? How do we join these two? Well, we join them by using kind of a symbol that looks like this, and this is what's called the union symbol. All right, and it basically ties together two sets. All right, it says, hey, take this set and kind of marry it up with this set, and that is the entire set of elements that represent, or numbers, that represent the range of this function, the union symbol. Puts them together. All right, let's do some more work with piecewise functions. Translating to equations. Not only should we be able to graph piecewise functions when we are given their equations, like in the last one, but we should also be able to translate the graphs of these functions into equations. And this can, of course, be a little bit more challenging for students, so let's take a look at one. Exercise number 2. The function f of x is shown graphed. Write a piecewise linear formula for the function. Be sure to specify both the formulas and the domain intervals over which they apply. Now, it should be pretty obvious here. We've got 3 lines, right? We've got this original slanted line that's going up, we've got this horizontal line that's going over, and then a slanted line that's going down. So we're going to need 3 different formulas, the easiest of which is going to be the horizontal line, but we'll get there in a moment. So first, let's talk about this particular line. Now this line starts at a point of -8, -5. Right, so the first line starts at -8, -5, and it goes all the way to -2, 4. Now we've already worked previously in this unit for how you come up with the equation of a line if you've got 2 points. So one way to attack this problem is to simply just take these 2 points, calculate the slope, and calculate the y-intercept that you would get with these 2 lines. So for instance, for my slope, right, I can say that that's 4 minus -5 all over -2 minus -8. That's going to be 9/6, and that's 3/2, right? We could also tell the slope graphically by looking at the line and sort of coming up with some additional points on it and saying, oh, well, we have a run of 2 and we have a rise of 3. And that's perfectly fine, right, if you're just trying to come up with this thing. Now, the y-intercept, how do we come up with that? Well, there's 2 ways to do that as well. One way to do it is say, well, all right, let me just take this thing and say I've got y equals 3/2 x plus my y-intercept b, which I don't know yet. And now I could take either one of these 2 points and substitute into this equation to figure out what b is. Let's go through that procedure. Let's do -2, 4. So I could take this thing, I could put 4 in for y, I can put in -2 for x, and now do a little cancellation there, and I'll get b is equal to 7. And so the formula for that first line is y equals 3/2 x plus 7. And you might say to yourself, well, that doesn't look like it's got a y-intercept of 7, except if I take my ruler out and I kind of put it along this line and I just extend it, maybe I do some dashed lines afterwards, then what I see is I see a y-intercept right there at 7. And that's a very legitimate way, especially let's say that this was a multiple choice problem and they gave you, 4 different choices for what the piecewise function was for this particular graph. Well, one very legitimate way of figuring out what the y-intercept is taking the line and extending it until it hits the y-axis and saying, oh, there we go. We've got a y-intercept of 7. All right, so here's my formula for the first part, right? That's part number 1. Now part number 2 goes from this -2, 4 all the way over to 3, 4. All right, so from -2, 4 to 3, 4, we just have a horizontal line. Now, for a horizontal line, the y value is constant, and in fact, that constant y value is y equals 4. So in this part of the formula, we simply have y equals 4. I'm just going to circle these for the time being. All right, there's nothing more I need to do on that. Remember, horizontal lines have y equals a number equations. Vertical lines, however, have x equals number equations. Now, the final part of this formula, right, is this one. The one that goes, and let me extend this page a little bit, the one that goes from 3, 4 to the point 6, -2. Now this one I could do exactly the same way that I did the first one. I could come up with the slope and the y-intercept based on this. But why don't we do this one all graphically? So for this one, right, let me take a look. I've got this point, this point, this point, and this point. Looks like I am going to the right 1 and down 2, to the right 1 and down 2. So here I've got a slope, right, of -2 or -2 over 1, depending on how you want to look at it. Tried to erase that and it didn't quite work. And now let me find that y-intercept like I did in the previous problem by just simply kind of extending my line and seeing where it hits the y-axis. So I just use my ruler. It looks like I'm intersecting the y-axis up here at 10, which means the y-intercept of that line is 10. And there's my formula for the last portion of this. Now I haven't actually written out the formula yet, so let's do it. Right? We write it like this: f of x equals, big parentheses. I don't state y equals because that's what f of x is. I'm going to say 3/2 x plus 7. Now what is my domain interval there? That goes from -8 to -2. Whoops. So I'm going to say -8 is less than or equal to x, which is less than or equal to -2. You could also use interval notation there. You could totally put a square bracket, -8, -2, square bracket. That would be fine. Move this out of the way. Bring this thing back up, hopefully, where it's going to get in the way again. My second formula is that constant, right? Y equals 4. Now that goes from -2 less than x less than or equal to 3. Remember, we're talking about x values here. And my final formula is -2x plus 10, and that's going to be 3 less than x less than or equal to 6. All right, one little note before we move on, because this might be something that some of you are wondering about. Why did I choose to put the equality there and not there, right? Or why did I choose to put it there and not there? And the answer is, in this particular problem, it actually doesn't matter. Now, some math teachers would probably be angry at me for saying this, but I claim in this particular problem, you could put it there or there and there. You could have the equality on all of these things because, remember, the fundamental definition of a function is that it is a rule for a given input, there is exactly one output, right? And the plain fact is when x is equal to -2, this formula is going to give you 4, and that formula is going to give you 4. And when x is equal to 3, this formula is going to give you 4, and this formula is going to give you 4. So it really doesn't matter where the equality goes in this problem, and that's because our graph is continuous. There is no open circle. There's no jump or discontinuity in this particular problem. All right, let's work a little bit more with some piecewise functions. Now, let's talk about dealing with the algebra of piecewise functions. Piecewise equations can be challenging algebraically. Sometimes information that we find from them can be deceiving because of these domain intervals. So let's take a look at a cool example of this in exercise number 3. Consider the piecewise function g of x equals 5 minus x for x less than 2, and 1/2 times x plus 2 for x greater than or equal to 2. Letter A, determine the y-intercept of this function algebraically. Why can a function have only one y-intercept? All right, so to begin, I'd like you to pause the video. We've talked plenty of times about how you find the y-intercept of a function. Go ahead and do that. Now, if you're the person who, with equations of lines, says, well, the y-intercept is the number that's just sort of added on, then this problem becomes a headache for you. But if you're the type of person that says, well, I know that the y-intercept is the output when x is equal to 0, then it's a piece of cake, because you're just looking to evaluate g of 0. 0 falls in this particular interval, so that's going to be 5 minus 0, and that's 5, right? So the y-intercept is 5. Now, second part of this question, why can a function have only one y-intercept? And that's simply because a function can have only one output for any input. Specifically, specifically, this is why I'm a math teacher, not a spelling teacher, specifically for x equals 0. All right, so, the plain fact is the y-intercept is defined algebraically as being the output of a function when x is equal to 0. If it had two y-intercepts, that would mean it had two outputs for when x was equal to 0, and therefore would not be a function. But now let's talk about x-intercepts, because they're a little bit different. Letter B. Find the x-intercepts, the zeros, of each individual linear equation. All right, great. So now a function can have as many x-intercepts as you want. 0 all the way up to an infinite number of x-intercepts, and yes, there are functions that have an infinite number of x-intercepts. We'll get into those later in the course. But in order to find the zeros algebraically, what you do is you take each one of these equations and you set it equal to 0 and solve for the value of x. So pause the video right now. You're going to find two zeros for this function. See what they are. All right, let's go through it. So for the first one, right, very simple. We have 5 minus x is equal to 0. Subtract a 5 from both sides, and we'll get negative x is equal to negative 5, and that, of course, leads to us saying x equals 5. The other one, a little bit more challenging, 1/2 x plus 2 is equal to 0. Subtract 2 from both sides, we'll have 1/2 x is equal to negative 2, and multiply both sides by 2, and we'll have x is equal to negative 4. So there is no question that when I take x equals 5 and I substitute it into this formula, g of x is equal to 0. And if I take negative 4 and I substitute it into this formula, g of x is equal to 0. So they appear to be zeros of this function. But let's take a look at graphing this function. We're going to take a look at a little bit of a different way of graphing it this time. So, letter C. Graph the piecewise linear function below by first graphing each individual line in dashed form and then making them solid based on the domain intervals. All right, so there are two ways that you can go about graphing a piecewise function, at least two ways. One way is what we did in exercise number 1. We create a table of values, we plot points, etc. Another kind of nice way to do it is to totally ignore the domain intervals. All right, and here's what I mean. So the first one is y equals 5 minus x, right? Which is the same as y equals negative x plus 5. All right, in this particular case, we would have a slope of negative 1 and a y-intercept of 5. So if I were going to go about plotting that, I might just come up here, go to the right one, down one, to the right one, down one, etc. Right? And that's going to be this particular line. Now, instead of drawing it in solid, what I'm going to do is I'm going to take my ruler, okay, and I'm going to draw a dashed line through these points. Okay. In mathematics, a dashed line is simply a guideline, right? And we've seen dashed lines before when we've graphed linear inequalities in two variables in Algebra 1, right? Dashed lines basically are there as a guide, but we're not saying that they count for anything. Now, the second line, y equals 1/2 x plus 2, this one I don't have to rewrite, that one has a y-intercept of 2 and a slope of 1/2, so I go to the right 1 and up, right 2, up 1. All right, so I get a bunch of these points. There's a little basic line graphing. I'm going to do exactly the same thing that I did before. I'm going to draw this line in dashed. And again, nothing yet counts, all right? According to the way the graph looks right now, I haven't graphed a single thing because it's all dashed. Now what I'm going to do is I'm going to look at this and I'm going to say, okay, that formula applies for every x value that is less than 2. Every x value to the left of 2. So I come over to my graph, I go to x equals 2, that's right here, and this particular thing I'm now going to fill in solid. All right, nice solid line. Now my second formula, this one applies for all values of x greater than or equal to 2. So all values of x to the right of x equals 2, and that's all of these. And I'm going to draw it like that. Now, if you've been graphing in pencil, you could easily come back and erase the dashed lines, but you don't need to. There's absolutely no need to do that because dashed lines in mathematics are regarded as just being guidelines. We don't assume that those are part of the graph at all. So the graph of my function is now this kind of a little bit asymmetrical V-like shape. Okay? Let's keep going. Letter D. Let me get this out of the way and actually bring this all the way up to the top. Here's that graph again. Letter D. Why does your graph contradict the answers you found in part B? So in part B, right, we found that we had zeros at x equals 5 and at x equals -4. So why does this graph contradict, right, what we found in part B? Pause the video now and see if you can give me an explanation. Now, I'm not asking why it happens. I'm just asking, like what do you see that's like contradictory here? And what I see is that when I look at this graph, the solid filled in portion, there are no zeros, right? The graph has no zeros, even though the algebra found 2 of them. Right? So using our algebra, we found zeros at x equals 5 and x equals -4, and yet the graph, remember, which is only the solid portion, found, there's no zeros on that. It never touches the x-axis. So let's look at the final part of this problem, letter E. How can you resolve the fact that the algebra seems to contradict your graphical evidence of x-intercepts? All right, so keep in mind, in this particular formula, we had a 0 at x equals 5, and this particular one, we had a 0 at x equals -4. So think about how we can resolve that conflict, that contradiction. Pause the video now and think about this for a moment. Well, it's kind of cool, right? In this first formula, which only applies when x is less than 2, the 0 is at x equals 5. So this formula doesn't apply at the location of the 0. Likewise, this formula only applies when x is greater than or equal to 2, and we had found a 0 at x equals -4. In fact, we can see those zeros on the graph, right? Let me make them in red, just so that we can see them a little bit more obvious. right? Here's that 0 at x equals negative 4. Here's that 0 at x equals 5. So the zeros that we found didn't fall into the domain intervals for which the formula is applied. The zeros don't fall in the domain intervals. I mean, if they had been reversed, if 5 had been down here and negative 4 had been up here, then we would have seen them on the graph. But the plain fact is, neither one of these are zeros because this formula only applies when the x values are less than 2, and this one only applies when the x values are greater than or equal to 2. Let's take a look at one more problem that kind of tests that idea. Exercise number 4. For the piecewise function f of x equals negative 2x plus 10 for x less than or equal to 0, and 5x minus 1 for x greater than 0, find all solutions to the equation f of x equals 1 algebraically. All right, well this time we're not looking for zeros, we're looking for ones? I don't know, whatever. We're looking for the x values that give us a y value equal to 1. Pause the video now and see if you can find, well, any at all. Maybe kind of like that last problem, there aren't any. Let's see what you can find. All right, well, I'm going to take that first formula, negative 2x plus 10, and I'm going to set it equal to 1. So let me subtract 10 from both sides. All right, we're going to have negative 2x is equal to negative 9. Let me divide both sides by negative 2. And we're going to have x equals 9 halves, which is the same as 4.5. Now, that seems like it's an x value that would give me a y value of 0, except this particular formula only applies when x is less than or equal to 0. And since 4.5 is not less than or equal to 0, we will reject this one. It's an extraneous root, we say. We reject it because not in x less than or equal to 0. All right, so that one's out, right? That is not an answer. Let's take a look at the next one. So we can also say, well, 5x minus 1 is equal to 1. Add 1 to both sides, we'll get 5x equals 2. Divide both sides by 5, and we'll get x equals 2/5. Now, does 2/5 fall into the interval x greater than 0? And the answer is absolutely. Yeah, this one's good. So this one is good because it does fall in the domain interval. All right. So the point here, the algebra of piecewise functions can be tricky, not because the algebra itself is tricky, but because answers that you get always have to be checked compared to the domain intervals that are given for each formula. All right, let's wrap this thing up. So functions, right? Rules that give outputs for given inputs. They come in equation, table, and graphical form. And yet, sometimes those functions will have more than one equation that applies depending on what the values of x are that go into the equation. As an aside, the United States Federal Tax Code, Income Tax Code, is a great example of a piecewise formula. Because if your income falls in one given range, one formula applies, a different range, a different formula applies, another range, another formula applies, and literally there's something like 5 different domain intervals depending on whether your yearly income is between 0 and like 15,000, between like 15,000 and 30,000, etc. I'm not sure that those values are exactly right, but it is a great example, and it also happens to be piecewise linear, in fact, and it also happens to be a continuous piecewise linear function. Now, we saw how to graph piecewise linear functions, also how to come up with the equations of piecewise linear functions if we're given the graphs, and we also looked a little bit about how the algebra of piecewise functions can be a little bit complicated because of those domain intervals. We'll be seeing piecewise functions on and off as we go through this course. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.